Good morning. Welcome to US-Japan Research Institute seminar on the topics of technology against disasters. My name is Katsuichi Uchida, President of USJI and also Vice President of Waseda Universities. USJI was established jointly by 5 leading Japanese universities, namely Kyoto, Keio, Ritsumeikan, Tokyo, and Waseda, in order to provide policy-related academic research results to wider audiences here in the United States. We have office at 1875 High Street. Since the inauguration seminars in March 2009 in Tokyo, every September and February, we have USJI Week here in Washington, D.C. This and the last weeks, under the general title of the Reconstruction after the Great East Japan Earthquake, we have 5 seminars, 2 collaborated lectures, open house, and social networking receptions. This morning, we have Seminar 3, Technology Against Disasters. Japan produces many efficient and competitive manufacturing goods, like automobiles, computers, and so on. And so we produce 6 prime ministers within 5 years. We are proud of our high productivities of prime ministers. September 2009, as the first USJI Week, Prime Minister was Mr. Hatoyama. Last September, Prime Minister was Mr. Kan. This time, Prime Minister is Mr. Noda. Among these 3, 2 of them are graduates of our member universities, University of Tokyo and Waseda. This morning, as I've said, we have seminars on technology against disasters. We are very pleased that Professor Hashimoto, Vice Chair of USJI, as well as Vice President of Waseda University, is a moderator and panelist of these seminars. And we are also very fortunate to have 3 distinguished speakers from the United States, as well as specialists on robot, and natural disasters. So I would like to ask Professor Hashimoto to moderate this session. Professor Hashimoto, please.
Thank you very much, Professor Uchida. Good morning. Today, I'm very happy to have a seminar about the technology against disasters. So in this opportunity, I would like to talk about the technology and science of the future of society. And at first, to keep the time for the discussions, I asked all the speakers to keep the time up to 20 minutes for each talk. And I prepared, unfortunately, about 26 slides, so I have to skip some slides and to talk about what I want to say and to initiate the discussions. So my talk is, the contents is a self-introduction. I'm working on the robotics and the information science and mechanical science. And next I talk about the shock of March 11 and also about the future of science and technology, especially against disasters. So this slide shows the many robots developed in a university since 1970. The Waseda University is famous in Japan and also in the world about research about human-type robot. But not limited to the human-type robot, we are developing many different types of robots. So about my laboratory, in my laboratory about 30 or 40 graduate students working, researching about many different fields of science and technologies, especially for the image processing, the multimedia processing group, and the algorithm is a basic theoretical research about knowledge science and the machine learning. And to integrate all other groups, that we have a very big robotic group. So we are developing a humanoid robot and autonomous robot, and also another robot, something like a building inspection robot. So about the robot application, we have many experience about application of robot in the secondary industry that we call it industrial robot. So in this robot, the relationship between machine and materials is very important. And these 20 years in Japan, another application for the primary industry, including agriculture and also the forest caring robot, is now very popular. So in this area, machine and natural environment relation is very important. And these 10 years, the third industry, we call it service robot field, become very popular, and we are expecting to make a new industry for the service robot. In this area, the relationship between machine and human is very important. So especially in Japan, 1/4 of the population are aged people. So we are now, many people are researching about assistant robot that can assist aged people. So about the direction of the robot, as I said, secondary industry is very important application area of robotics, but now we are entering a new field, robot research, beyond production machine. And next is beyond software simulator. We can use a robot to simulate the actual scene of the life and also the society. And also, another application is beyond graphical user interface. You can use a robot as like a computer interface. So the robot is something like a computer with body. And also, another last application field is beyond multimedia. Robot is itself embodied media, so we can use the robot much more wider application area. So in a university from 2003 to 2007, we operated a very big project. We call it 21st Century Center of Excellence Program. That's supported by Japanese government. So in this project, in a university, we try to create a new society supported by robot. So after the 21st Global COE Center of Excellence Program, we started the next project. We call it the Global Center of Excellence Program, also supported by Japanese government. So in this project, we have 3 groups. One is a personal, physical, and psychological robot group. And the second one is community connected and co-creative robot group. And the third one is social, secure, and safe robot group. So about today's topic, the third group is very related to the robot application against the disasters and security. So this global COE program aim to establish a new research area of the robot to combine all the aspects of the robot engineering. So we call it methodical robotics. So to establish the structural robot studies to create new practical technology. Some applications we created in recent years. The most is mobility for the elderly people, and another is for the medical application. And also, we make a new house that is safe and secure for the aged people in the beefy area in the middle of Japan. And we also make another type of robot that can help the elderly people. The help, the psychological help, mind help, and also the physical help that the robot can do. And also, we are doing very basic research to develop element technology of the robot, including chemical robotics. It's a chemical reaction system. Instead of machine, a mechanical machine, we can use a chemical reaction system to make a robot. This is just a beginning, but we succeeded to create something like an inch-long robot using gels. And also, in the middle of the slide, we made a vertical narrow space robot to inspect the very narrow space. This is vertical, so this slide is top view, so the robot can move in the narrow space. And also, we are doing the research about the theoretical and also basic research about something like signal processing. This is monaural sound separation. This is the original sound. We have only one single channel sound, and then the robot computer software can separate from only one sound source to and the third one. So this is a very basic technology, but very useful to make an intelligent robot that can be used for the disaster forecast. And also, the machine learning is another very essential problem technology to make the robot with intelligence. So we are considering we are entering a new research phase of the robotics called future. That I call it showtime is ending. So far, the many robots have been developed, but only for 5 or 10 minute demonstration at the end. But from now, in the future, we have to use the robot for safety and secure and also with low energy consumption. So the robot should work 24 hours with non-stop operation. That all weather type robot must be developed. So, and also no license required and extended robotic technology must be used to build a secure environment, and maybe can be used to make tools and furniture. So the next slide, I'd like to talk about the shock of the March 11, 2011. We know now what has happened, and what happening, and what will happen. This is a very important issue. So before talking about the East Japan great earthquake, I want to show some slides about the seismometer. 2004, the magnitude of the earthquake was 9.1, and maybe more than 220,000 people were killed or lost. And in Haiti last year, this magnitude was 7, but also more than 200,000 people were killed. And in Japan, in Hanshin-Awaji, west of Japan, we had a big earthquake after 1995, with magnitude 7.3. And this time, about 6,600 people were killed. And this year, the March 11, we had a very big earthquake at East Japan. And it is not sure now, but 20,000, more than 20,000 people killed at this year. So, observing these earthquakes, I consider very much about what the result of the earthquake. Because I don't care about the many people that killed in these earthquakes, but I don't think that such a very big number of people killed in Japan, because the way I thought that Japan is an advanced country, so not so many people were not killed by the earthquake. This was my mistake. So I think that what that advanced country means, what is the technology, what is science advancement means against the disasters. This is my very big question. So to facing the big disasters, natural disasters, there is no difference between the advanced country and the developing countries. So I want to ask the question, what means advanced? What means advanced country? This is my very big question. So the future of mankind, there are many dreams we have. The system as a surrogate of human, system to extend human ability, system to enhance humanities. So we have believed that we are developing a new technology to realize our human dreams. But the human with artificial systems, what means it is? What will be realized? And where human will go? So this is my big question. About the disasters, and science and technology, there are many different phases. The before disasters, the foresight, prediction, forecasting, foretell is very important. So the science can do something about including technology of signal processing, measurement, and knowledge engineering. In the middle of the disaster, the fail-safe and steps to minimize the disaster is very important, and emergency function is also very important. The more important is after the disasters, the restorations, revival, preparing for the future, what we can do as a technology development and researchers, and planning, learning, understanding, and philosophy is very important. So today, I want to talk about such issues. So today, as a researcher of the robotics, I talked about a little bit about the robot we are doing research, and robot society, robot to make a robot society. What the natural science can do is mainly the observation, analysis, and understanding to model what is going on in our space. And from the viewpoint of engineering, we can apply the engineering result to make a robust infrastructure and make a physical effect to our society, and maybe the information, computer technology, communication technology, and robotic technology is very important, because IT is the soft, but the RT is hard. So both is very useful, and both is required to make a society more robust. And from the viewpoint of cultural science, the individual's the mind and body secure and safety can be saved with the result of the cultural science. And from social science, the policy and social system reconstruction can be applied by the social science result. So civilization, industrialization, and culture. So we have to create a new society that can sustain our happiness and also security control technology and strategy is very important. So we have to use all the results of science and technologies. So just after the earthquake of East Japan, the Waseda University established the Center for Research on Reconstruction from the Great East Earthquake in Japan. So director is Professor Kadawa, the University of Executive Directors, to recover from large-scale disaster and construction of a new social systems. In this project, we have three main themes. One is medicine and healthcare. And second one is infrastructure restoration and disaster management systems. And the third one is urban planning and social design. In this project, we concentrate all results of science, engineering, and human science and social science to make our society more robust and more secure. So thank you very much. And next, I'll ask Dr. Martin Bruera from iRobot. The iRobot is now very famous in Japan because iRobot robot assisted the very difficulties in the nuclear power plant. So, Martin, please.
Thank you very much, Professor Hashimoto, for your informative and inspiring presentation. We're just taking a minute here to plug in. Good morning. I'm with iRobot. I'm Martin Buehler. I'm the Director of Research for Manipulation and Mobility. It's a great pleasure here to be here with you this morning. I want to also thank Professor Hashimoto for inviting myself and Mr. Roy Rondo. We are splitting up the presentation between the two of us this morning. I will tell you a little bit about iRobot and the current robots in view of their use in disaster scenarios. And Mr. Rondo is an excellent speaker, and he's also very well suited to give this presentation because he was one of the very initial team of 6 people who went out to the Fukushima area in six days after the disaster occurred. So he'll give you some impressions of the lessons learned from those involvements. Japan was hit by a really terrible, terrible disaster. Our hearts really go out to the people of Japan and everybody who was affected by this tragedy. iRobot was able and is honored to have been able to contribute to some of the effects, to mitigate some of the effects. And we wish we could have done more. And we certainly hope we will be able to continue to help and do more in the future. My presentation, again, will be the first half on the current iRobot robots, some of which have seen action in Japan. And then talk a little bit about some of the research that feeds the pipeline for some of the future capabilities, which may also have effects and implications and support for disaster operations. Most of you probably know iRobot. We're a company of, in the meantime, over 700 people, so I get to work with 700 passionate, hard-working roboticists every day. It's a great place to work. We're all very passionate about robotics. The company, when I joined the company, a friend asked me, iRobot, it's some sort of a startup overnight success. You know, a lot of people still think this is a very short path to success, but the company was started in 1990. So I asked my friend, overnight success? This must have been a long night. Did you notice the 20 years of darkness since between the 2 days? So this also gives you an appreciation of how long it took the company and perhaps how long it really takes to have an effect to design and build and market a sustainable product in the robotics area. The product that you are probably most familiar with that our robot sells is the robotic vacuum cleaner, and the Packbot and the Warrior. Those were products that were started, that came about 10 years after the company was founded in the early 2000s. The company was put on the NASDAQ stock exchange in 2005. And is still, I think, the only pure play robotics company in the sense that it's the only company that is exclusively devoted to making robots and to making practical robots that people buy. Just in terms of distribution, we're an international company by now. We're located, our headquarters is in Boston. We have a few other locations in the US and several international locations as well. After I've seen the family picture of iRobot, all the heads, here's the robot family. We have two main divisions, the home robot division. The mission there is to build robots that clean your home so you don't have to, so you can spend time with the loved ones or play golf or whatever. The other side is the government and industrial side. Here we build robots that are suitable for military applications, but also police, first responders, and disaster relief. We're also finding use for scientific applications like the sea glider. So this is going to show you a couple of robots here. There's the sea glider. I'll talk a little bit about that a little later on. The Sea Ranger and the Transphibian, a biologically inspired underwater robot. And then we have our family of tracked robots, starting with a small, throwable 5-pound robot called First Look that we've just commercialized and will be selling very soon. Then these three guys here, Packbots and Sugby, of which we've sold over 4,000 at this point. So a lot of insight, a lot of iteration, a lot of heart went into these robots to make them successful. And very recently we have commercialized and productized a much larger version, the Warrior, weighs several hundred pounds, much faster, much more payload, has a very strong arm that can lift 100 to 200 pounds. This is a very quick, fast action video. I think this was put together by somebody who had, I think, a little bit of attention deficit syndrome. So it's a very, very quick action, but it's actually a very good summary of some of the robots, how they're used, what they look like, what they do. So you'll see there's a sea glider being deployed, Warrior going up some stairs, the Packable, a small unmanned ground vehicle. Here's First Look, very small, throwable, yet very mobile. Can get over a lot of obstacles, can also climb full-size stairs. This speaks to some of the ruggedness of the robots. They're waterproof, they can survive very high temperatures, and as you know, they can also survive even in a high radiation environment, even though they were not originally designed for it. They have a lot of capabilities. They have lights to see in the darkness. You can add night vision systems. This Warrior showing off some of its strength. Then the Packbot arm with its dexterity. They're able to get in a lot of places just to see what's going on. And here's First Look coming up again. Some of the high-level command interfaces we have developed to make the robots easier to use. We also increasingly endow them with localization and navigation so they can move around on their own. So they don't need second-by-second command and control. Here's a robot that is able to clear a whole minefield and make it safe for humans to go over the area. You have a civilian application that uses the Warrior arm reach. Again, the Warrior arm getting into tight spaces. Here's a Packbot neutralizing a bomb that may have been placed by somebody to wreak havoc. So this is a very fast-paced overview of some of the robots that we have today. One of the points I want to make, and one of the capabilities and abilities of this robot, or our robots, is that they're built to be very modular and flexible. And I think that's a very important property, especially for disaster robots, because you never know what disaster you're going to hit. So it's very difficult to design a robot from scratch, targeted at a disaster, because by its very definition, it's going to be different from the last one. So one approach is to have a very rugged, mature, capable platform, and then develop around it a large array of add-ons, and make the infrastructure structure so it's modular and easy to customize. And that's what we've done with PackPod, and that's what we're doing with Warrior and our other platforms as well. And that lets us provide these robots for many different applications, not just military applications, but sell to police and first responders, make them available when disaster strikes. But it's not just about hardware, you also have to have the software that has to match that. The software is just as important. So we've developed this aware, intelligent robot operating system that supports this digital modular architecture. So that when you configure a robot, the software is there to go along with it. So, and this software doesn't just support different personalities, so to say, of the robot, but it also goes cross-platform. So we use the same intelligent robot software on Warrior, on PackBot, and then in the future, the goal is to have them on all of our robots. This will also make it easier to use the robots because the operator interface is going to be the same, which is very important, again, for disaster robots, because there's no time to do training. Based on this modularity, we have a strong program to support third parties. There's a third-party developers kit where we make a ready off-the-shelf item available that plugs into the robot, that makes it easier for third parties to control the robot and add their own customizations, their own identity to the robot. So it can become a specialist for chemical sensing, for nuclear applications, for some gas scare. So it makes it easy to customize. And again, enabled by Aware 2. So robots have been able to mature and evolve through many deployments in Iraq and Afghanistan, for which they were originally built. But based on their ruggedness and based on these deployments, they have been able to save many, many lives, where they have been able to take bomb technicians away from the sphere and put distance between the people and the explosive ordnance that would otherwise could have harmed our soldiers. So this platform has saved many lives and has also matured now into a very hardened system, has 10 years of evolution, and has been deployed tens of thousands of times in explosive ordnance disposal missions. 10 years ago, there was not a single explosive ordnance team that had a robot. Today, every explosive ordnance disposal team in the military has at least one. Many have several. So it's so successful, it's become part of every team. So when this great tragedy happened, whose the 10-year anniversary we remembered yesterday, we also reached out very quickly and were able to make PackBots available in 2001 to search for survivors and also inspect partially collapsed buildings before people were going in. So again, we were able to support that because it was a platform that was ruggedized and was basically ready to go. But there was still in the early days, this day was sort of a watershed for robotics, as our COO, Joe Dyer, just recently said, in the sense that before 9/11, there were really no robots used in disaster response. This was the first time when robots pretty much were brought out of the lab and early prototypes, as PackBot was in those days, to show their mettle in this challenging environment. After 9/11, there have been robots pretty much at every major disaster helping the human teams. Last year, more recently, you will also remember the explosion that ripped through the BP rig called Deepwater Horizon, killing 11 workers, and by the time it was over, there was over $200 million of oil spilled into the Gulf of Mexico. Robots played a huge role in this. Being 5,000 feet underwater, when no person can go, there were dozens of robots right there underwater 5,000 feet trying to help figure out how to plug the hole, how to plug the leak. In the meantime, on the surface, people were starting to worry about where all the oil was going. Not all was on the surface, and there were questions about were there oil plumes. And BP, of course, initially denied that there were any such oil plumes. Very soon after the disaster, we had several employees from iRobot throwing a couple of sea gliders in the back of a pickup truck, driving down to Louisiana and launching them to help use this robotic technology, the sea glider, that's shown right here, to provide data to local researchers, so to analyze the data and help identify where the oil plumes were, how large they were, and what the density was. And you see some of the data, I won't go into details, that over time showed how the amount of organic matter that correlates to oil reduced over time. A quick word on sea glider. It's another technology that is originally developed for scientific purposes to track properties of the water column, and came in very handy in this particular disaster to use the basic platform that was then customized to track oil in the water at very short notice. I really like this technology because it has no moving parts. It means it can be very reliable. No moving external parts. It's really sweet. This technology we licensed from the University of Washington. It's called a glider because it glides just like an aerial glider. It can change its buoyancy to be heavier than water and sink, and lighter than water and drift up. In the process, its up and down motions, by the virtue of its two little stubby wings, it creates forward momentum. So it can traverse, and it traverses the water column in a zigzag motion. It can go all the way down to 1,000 meters. And when it gets up to the surface, it can put its tail in the air and call home via its Iridium satellite antenna, upload the data to the operators, and get more mission profile data if needed. By virtue of its operation, it's also extremely power efficient. It can go for over 10 months and literally traverse halfway around the globe on one battery charge. So this is one of the robotic devices in the arsenal that can be applied to various disasters. And then the purpose of this workshop here is, of course, the tragedy that occurred in March 2011, and I'll leave it to Mr. Rondo to talk about that in more detail. But let me just continue to talk just a little bit about research. Another, I think, interesting and important thing to keep in mind is when thinking about disaster robotics is when one employs an existing platform, one also can harvest all the research that is ongoing that goes into those platforms. And this is something that happens at iRobot. Another point is we at iRobot in the research group, we have about 33 people. We actually use primarily iRobot products and their modularity and their aware support to do our research. So we were able to customize the robots just like third parties would to do our research. And the nice thing about that is, being at iRobot is once we have some good results, it's fairly easy to transition those results to a product. And the same thing applies to anybody who uses our product as well. We do research in a lot of different areas. Let me just go a little faster here. And we're working on making the robots more intelligent, increasing their autonomy. We're trying to figure out how to make robots work together more effectively, make better robots, and make them easier to use, human-robot interaction. In the area of autonomy, we have packaged a lot of the stuff that's needed for autonomy: computation, communication, and sensing, together with all the smarts, like SLAM and navigation, localization, perception, into one box that we call the aware head. And you see some of the things you can do. It enables high-level interfaces, so the operator sees a map where the robot is that the robot created, and can control the robot by simply clicking on the map, and the robot goes there. The operator does not have to move the robot around with the joystick, even though that's a pretty good interface for teleoperation. But can simply put a dot on the map, and the robot will magically figure out how to get there. Avoid running into things, avoid running into people. The robot gets stuck, it will replan. We can do that seamlessly indoors, and then go outdoors and use GPS. And of course, indoors is no GPS. And so this was one example of the many projects we do on making the robots more intelligent, more autonomous. We want also the robots to be much easier to use. When you're working on a disaster, you don't want to have a lot of people dedicated to controlling the robot. You want to take those people and put them to better use. So we want more natural interfaces. Here's an early example of what we developed a couple of years ago with Brown University. We work a lot with universities. This is a robot. You see it's a PACBOK, and we actually use its modular interface where we plugged in a actually this is the standard arm, but we plugged in additional computation. It's very easy. And use a flash LiDAR to do person tracking, gesture recognition, and it also has a bi-directional voice recognition interface. So here the operator says, go through the door, the robot does it by itself, it senses the environment, the operator verbally says, oh, stop, change my mind, come back. The robot acknowledges, yes, I heard you, you want me to come back. The robot comes back and picks up again the person following. So this is a very simple, but sort of gets you the idea. You want to tell the robot, go fetch me that. And the robot understands you're pointing what you're pointing at, and yes, the person wants me to fetch an object. So we're doing similar things with person following the vision, and that has found its way into our latest AVA platform. I'm not talking about this here, but earlier Professor Hashimoto was talking about telepresence. We've just developed a prototype of a app-ready robot that is ready to work in close proximity to humans as a telepresence robot. So that person following found its way into that robot that was the person following that was developed in the research group. We're working on various versions of collaborative unmanned systems. I want to just point out one version here that we did recently with AeroVironment that combines a ground vehicle, a PACBot, with an aerial vehicle, the Raven. It's a very potent combination because the two have very heterogeneous capabilities. The bird has the eye in the sky view, and it also has a very good communications link to the robot because it's line of sight. The robot on the ground can do things the bird can't do. It can sniff things to see if there are any explosives. It can read license plates. It can go into buildings to see if there's any damage or if there's anybody in there. And the two share all the information. They share the maps, they share a link to the operator. In terms of new platforms, one of the many examples where we're building new platforms is this Transphibian. This could be a very potent platform for underwater inspection in case of a disaster. It's highly maneuverable. It can hold on to things. It is very good with station keeping, and it can crawl out of the water. That's why it's called Transphibian. I talked earlier about the benefits of using existing platforms because we can harvest other groups' work on that platform. There's an example where we've gotten some funding to look into track-like suspensions that improve the mobility of our track platforms potentially a lot. Looking at tank tread designs and soft suspensions. And we've just built a prototype that has amazing mobility over rough terrain that is basically retrofittable on a PACBot. Most of our robots on the ground are mobile manipulators, so we're very interested and we do a lot of work on mobile manipulation. We've joined with University of Pennsylvania and University of Massachusetts at Amherst to develop completely autonomous manipulation routines that we're implementing for grasping and manipulation, including like picking up a key, inserting it into a lock, and then opening the door completely autonomously. Another example on the hardware side, we're very interested in developing a low-cost, rugged hand, a hand that is able to pick things up, has abilities to manipulate, but is also virtually indestructible. And this is sort of a fun kind of video that shows what we aim for indestructibility. Yeah. And my time is over. I just want to conclude. These are really not conclusions, but perhaps discussion points. Disaster response really requires many different robots. There's no standard disaster, of course. And so you really want to have a platform that you can quickly customize, and you want to have different platforms. You have quad roller, Ravens, PACBots, underwater vehicles, so that you can draw on whatever you need for that disaster. And you want to use dual-use robots because, as Hashimoto noticed earlier, Japan's got a protective with prime ministers, so perhaps government programs are not always lasting as long as they should to sustain an effort from the ground up, even though that would be a very important thing to have. And then there's the possibility to harvest technology from research groups and from various existing platforms. Thank you. I'm sorry, I went a little over. Thank you for your attention.
Good morning, everyone. Ohio gozaimasu. My name is Roy Rondeau. I'm one of the international salespeople at iRobot. And today, I would like to talk to you about iRobot's direct experience in helping Japan with the nuclear disaster that occurred following the March 11th earthquake and tsunami. The company, as Martin described to you, has a history of responding to disasters with humanitarian aid. And after the earthquake, our CEO immediately made a decision to supply 4 of our robots, 2 of our PackBots that Martin talked about, and 2 of our new large Warrior robots to Japan. We shipped those robots along with a tremendous amount of accessories and tools and hardware, and 6 people. 6 of our top engineers went over there. I should say 5 of our top engineers and 1 salesman, and that was me.
Top salesman.
Yeah, well, I'm an engineer too, but probably more of a salesman. We went over to Japan to deploy the robots and get them operational and to train people on how to use them. Now, when we shipped the robots to Japan, we had no idea who was going to use them. The company received the request. Our CEO, Mr. Engel, said, let's help, and we shipped robots over there. But at the time, we didn't know whether they would be used by the military, by the police, by the disaster relief agencies. It turned out that they were assigned to be used by the Tokyo Electric Power Company, known as TEPCO, at the Fukushima nuclear site. And we commenced training of those people. As Martin pointed out, the company has a history of responding to these types of events. We responded at 9/11 in New York, the Gulf oil spill. The top right-hand corner is a law enforcement application in Massachusetts where there was a suspected bomb, and we provided robots to the state police to help them defuse that bomb. And of course, Fukushima Daiichi. So here's a short timeline of what happened over the past few months. We continue to provide ongoing support for TEPCO. Personally, I've made 5 trips to Japan since March. I'll be going again at the end of this month. We have sent our engineers back to Japan to train the people, because one of the challenges that we had when these robots were delivered to the TEPCO people, they had never seen a robot in their lives. They had no idea what they could do, how they could be used, if they would be helpful. We also, so we had to train them, and it took quite a bit of time to do that, and we've continued to provide ongoing support for TEPCO. The robots have been very successful in assisting with TEPCO in working within these 4 buildings that were heavily damaged by the earthquake and the tsunami, for doing radiation measurements, for doing reconnaissance to survey the amount of damage inside, and by doing radiation mapping, and I'll show you some of that. One of our concerns was will the robots withstand the radiation in these buildings? Because honestly, we had never tested these robots in high radiation environments. We had never been asked to do it, even by our US military customer. So when we brought the robots over there, we said, we don't know. They may last an hour, or they may last a week, or longer. Well, I'm happy to say they're still working every day. The robots are used almost every day by the TEPCO people. They've been in some extremely high radioactive environments. There was one back in early July where we measured 4 sieverts of radiation, which if a human being is exposed to that level, you would be dead in about 90 minutes. So what were the challenges that we faced when you talk about responding with disasters or to disasters, and how robots may assist with that? Well, first of all, we had serious language barriers. The engineers that we sent over, of course, are English-speaking. The TEPCO engineers, for the most part, only spoke Japanese, but they were a really great team of people, very dedicated, and we had a good time training them. We needed very, very rapid response. Obviously, this disaster just occurred. It was chaos at a place like Fukushima. People were worried about radiation leakage, and we wanted to get the robots installed and operational as quickly as possible. As Martin mentioned, we feel that the things that allowed us to be successful here were that our robots are very easy to learn. They have a game-style controller, which you see down on the right. It's a standard Xbox controller. And of course, a lot of people today grew up in the video game generation. I am not one of those. But they learn to use these robots very, very quickly. I tell the story that I sometimes will bring a robot home on a weekend so I can practice on getting better using it. And my neighbor's 11-year-old son does a much better job than I do at driving that robot. The common software that Martin mentioned is also a key to these robots. It's a very graphical user interface that shows the operator all the views of the different cameras, where the robot is going, and what it's looking at. So it makes it very easy for a person who's never seen a robot before to come up to speed quickly in learning how to operate it. When it came to using the robots at Fukushima, first of all, we had no direct access to the Fukushima facility. We were prohibited from going there because of the danger involved. So we had to do all of this kind of remotely, train the people to the best of our ability, and then say, kind of, good luck, and stand back and help them with telephone and email and this type of support. We didn't know how the robots would be used initially. And as I mentioned, we didn't know how the robots would withstand the radiation. We've been successful because we can equip the robots with many different types of payloads. It's what you can put on a robot that makes it successful. And I'll show you some of the tools and accessories that we used. Now let's go back. You can see up in the top, that we equipped the packpod with a radiation sensor because they said the first thing they want to do is get inside of those buildings and see where the radiation leakage is. So we've done radiation mapping, we've surveyed damage, we've been able to remove some of the debris from inside the buildings, and we can monitor the recovery efforts that are going on. What happens is the robot team, as they're known now at TEPCO, gets requests from some of the other groups at Fukushima that they want to do a certain job. And so the TEPCO people will spend about 3 or 4 days practicing how to do that routine. Now, there are 6 buildings, 6 reactors at Fukushima. 4 of them were heavily damaged. 2 of them were not. And so they used the undamaged buildings to rehearse missions that they want to try to accomplish. They do about 2 to 3 missions per day, and each mission ranges about 2 hours. And you can see some of the first photos of when the robots went into these buildings. This was the first time since the earthquake that they had a view of what it looked like inside of those buildings. This is a view of a map that was created inside one of the reactors. And you could, the reason that TEPCO wants to create these maps is so they know if they can send people into these facilities and how long they can stay inside that facility before they exceed the dosage that people can tolerate. So the robots go in and do radiation measurements, and then they create a map of the inside of the reactor site so they can see specific radiation levels. On the bottom 2 slides, you see what is called a gamma camera. They mounted a gamma camera on our big Warrior robot and brought it up to the upper levels of one of the buildings to go in and see where sources of radiation are leaking from the containment vessels. Now we're able to do this because our robots are designed to be very, very flexible. We can put radiation sensors on them. We can put cameras on them. We can put gamma ray detectors on them. We can put explosive detectors on them. And of course, all different types of manipulating arms and grippers to pick things up and move things around. The other challenge that we faced was communications. These robots are teleoperated, in other words, radio controlled. Well, radios work real well when you're out of sight, out of doors, and you have a very clear line of sight. They don't work so well inside of shielded buildings. So radio communication was a big, big issue. Our robots can be operated by radio. They can also be operated by fiber optic cable. So we equipped the robots with about 200 meters of fiber optic cable, which allowed them to drive inside of these buildings and still maintain good levels of communication. We also, since then, have developed several other radio communication techniques where we bring a radio, use one robot to carry a radio inside the building, and then that radio controls the other robot that's inside the building. So it's kind of like a relay. And this has allowed TEPCO to go up to the 2nd and 3rd floors of inside each of these reactor buildings. So having flexible and robust radio communications and different alternative ways to achieve that are very important when you talk about what you need in a disaster robot. When we did this, of course, we didn't have any agreements with TEPCO or anyone else in Japan. There were no contracts, there were no purchase orders. We just brought some robots, all right? So this creates challenges in some ways, especially after some periods of time, people start asking, well, who owns this robot? Is it ours or is it iRobot's? So we've had to, over time, transfer ownership, formal transmission of the ownership of the robot between iRobot and TEPCO. But at the time, there were no contracts in place. We had very, very limited communications at the disaster site. There were no cell phones. There was one fiber optic link between Fukushima and the TEPCO headquarters in Tokyo. So when the people went into Fukushima, the TEPCO people, they were out of contact until they came back out. It was very difficult to communicate in the first month or so. That has gotten a lot better, of course. We have export licensing requirements. Our robots are very, very tightly controlled by what are called ITAR regulations. It's the International Trafficking of Arms regulations, and usually require U.S. export licenses for us to be able to export them to foreign countries. Well, when we made the request to donate these robots to Japan, we got the license in one day, which is, for anyone who's ever been involved in export licensing, is just unbelievable. Since then, we've done a lot of follow-on training with people. For the first month, we had daily teleconferences with our people in Tokyo. Every day, 7 days a week, we would have a teleconference between Japan and iRobot to make sure everything was going right. If we needed to ship more equipment over, we did. That allowed us to have the technical support and the ongoing support that's been required to make sure that TEPCO is as successful as possible. We shipped over 12 crates full of spare parts because, again, when you go into a disaster, there is no way to anticipate what you are going to need. In this case, when we found out that robots were going to a nuclear site, having nuclear radiation detectors was key. But we didn't know that when we first went in. So having a robot that's got that capability to easily change from one payload or one mission to another has been one of the big reasons for our success there. And we were very fortunate to have a very strong Japanese company as our distributor in Japan prior to this event. The company is called Sojitz Aerospace. They're a very well-known, large trading company, and Sojitz and the Sojitz people have been instrumental in helping us with this effort. So, what do you need? What are the requirements that you should think about when you're thinking about disaster robots? Well, here's what we've learned. First of all, flexibility. Have what we call a multi-mission robot, a robot that can be changed very easily to adapt to the particular disaster that you're responding to. You do that by having open software architecture. This allows not only to be able to switch payloads on the robot easily, but it allows for future developments too. And I think Martin mentioned that we give our customers the ability to develop their own payloads on a robot. So in the future, we hope to provide robotic platforms to Japan and let them Japanize them, make them Japanese. Have a robot that's operator friendly and easy to use and easy to learn. You know, thankfully, disasters don't happen very often. So even if you have well-trained people, they forget sometimes. And they may not use the robot for months or in some cases years. But when the disaster happens, you want them to be able to respond and respond quickly. And have a robot that's easy to use is a key part of that. Field proven. We have over 4,000 robots deployed in extremely harsh working environments, battlefields. And of course, the goal of any robot is to allow the robot to do things that are dangerous for people to do. So you want to have robust radio communications to keep the people as far away from the actual danger as possible. Rechargeable power sources. Our robots will operate on 4 batteries for up to 8 hours of operation. You want to have good cameras and multiple cameras so that the operators can see what's going on in all different directions, whether it's day or night or thermal imaging. You need that type of capability. And you want to reduce the need for people to be involved in handling dangerous situations. And of course, you want to be prepared for the future, whether it's terrorism or another natural disaster. So what we like to say is save a life and send a robot. Thank you. Let's do one more thing here. This is a video of a short video of the various missions that we ran at Fukushima. It's showing the packpot being operated here by the TEPCO people, and they use the packpots in teams to go inside. So one robot is watching the other robot. And here they're reading one of the radiation measurements on the system. This is measuring steam coming up. This is 4,000 millisieverts of steam, extremely high radioactivity, and very, very dangerous. This is the Warrior with a vacuum cleaner on it. I call this the world's biggest Roomba. And they brought the vacuum cleaner into one of the facilities to vacuum up water and dust, which went into a containment vessel to be disposed of safely. So those are just a few examples of how the TEPCO people have used our robots. Again, thank you very much for your time.
Thank you very much. The last talk will be given by Stephen McCabe from NIST, from another viewpoint. He's a specialist of the construction and earthquake and structure engineering.
Well, I feel properly humbled. First of all, konnichiwa. In my earlier days, I was asked to go to 3 Mile Island to do basically the kinds of things that the robot was doing at Fukushima Daiichi, so I guess I could say I've been replaced by robotic technology.
Couldn't happen to a nicer
Yeah,
man.
thank you. So I have no robots, no videos, and I'm not there at a disaster incident. I'm basically looking at the post-mortem and towards the future. So this is kind of the next steps, I guess you'd say. I work at NIST, which is one of the 4 NEHRP agencies, National Earthquake Hazard Reduction Program. More about that in a minute. We'll talk about some of the challenges that exist, a little flag waving with NEHRP, some of the research items, and the very sound partnership that we have with Japan. It's a difficult problem if you're dealing with seismic issues, as Japan has found out over the years, and the U.S. also. There's a lot of unknowns in terms of where the earthquakes may occur. This is particularly true in the eastern U.S., as we found out 3 weeks ago. There's a lot of uncertainty in terms of the ground motion. And not all earthquakes are of the same Richter magnitude, but in terms of engineering, they can have radically different characteristics. But if I'm an engineer trying to design for that, that complicates my life. There's a lot of uncertainties in terms of how the structure responds to the input ground motion. Soils can play a part, as well as just the basics of the structure and the ground motion. We don't necessarily know how much response or damage may occur. We have to design for enough capabilities, but you can't design everything to be completely damage-free. We couldn't afford to build anything. So we have to be able to translate what we know into new design rules for new design documents for structures as quickly as we can, based on research and investigating earthquakes that have occurred. It also leaves a big question about what about the existing inventory that's out there, like this hotel. Older buildings are designed to earlier sets of rules. What do you do about that? And as has been mentioned, there are tremendous costs to society, not only in terms of the damage, but in terms of the economic losses. There's large costs in terms of rebuilding. There are issues in terms of educating the population, in terms of correct responses, educating them in terms of investing in mitigation efforts, and how you fit that into tight budgets. If you look at Chile, this kind of shows you what we're up against. Here's Santiago, here's Concepcion, this is the lower part of Chile. This is a typical earthquake ground motion, recorded on the right side at Santiago, on the left side at Concepcion. These are both removed from the site of the epicenter, but this is what an engineer looks at. These are plots of acceleration versus time, and 3 different directions for north, south, east, west, and up, down. I have to convert that into a design level for a building. This looks different in Santiago than it does in Concepcion because of the differences in distances, the differences in local soil characteristics. It's a complicated dynamics problem. You can also see in Concepcion that we had building B with minor damage, 13 stories. Building A, right next door, also 13 stories, significant damage. The one on the right, significant damage, 18 stories. So, what's different between these 3 locations? Well, could be the building, could be the local soil conditions, could be a lot of things. Could also be how the building was laid out. This is a famous building, the structural engineers down in Chile, that was a very interesting building. Unfortunately, interesting buildings can frequently not do so well when they're shaken. And so what you have are collapses over the upper parts of the building. And here's some close-ups of some of the damage. Not a good day. Again, a very nice-looking building, but one in which not everything was put together in a way that was able to withstand a very large earthquake. We continue to learn lessons from each earthquake. This is not a new problem. It's existed obviously for a long time. It's only until the last 40 years approximately that there's been a real quantum leap in capabilities. What we found works pretty well is a solution methodology that involves public and private partnerships in terms of governments and practitioners and contractors, academic and government researchers who can combine information. As I mentioned, researchers and practitioners, people discovering new things and then practitioners implementing them. New materials and methods for design and construction are incredibly important. There's new experimental and computational capabilities we didn't have 40 years ago. We didn't even have them 10 years ago that are out there. Ultimately, it becomes the purview of building codes and those that develop codes and standards to put these lessons and these capabilities into the rules so that new structures, whether they're in Tokyo or Washington, D.C., can be appropriately designed to withstand likely hazards. And then we have the existing building question, which is a significant one. In the United States, we've got, as I mentioned, NEHRP, which is a four-agency partnership. This is legislated by Congress starting in 1977. FEMA, NIST, U.S. Geological Survey, and the National Science Foundation, each bringing their own expertise to this. NSF doing basic research in engineering and the geosciences. USGS looking at more application-oriented geoscience kinds of things. FEMA looking at the disaster response and the implementation aspects. NIST basically bringing things together to influence building codes and practitioner approaches. So there's a number of roles here, and they kind of cut across the various agencies. And you can read this as well as I can, but USGS, NSF, NIST, and FEMA have roles that sometimes overlap, sometimes are independent. But it's a range of activities because this is a wide-ranging problem. At NIST, we have development programs for building codes based on research. We're doing a lot in performance-based design, which is the new frontier in terms of being able to design things in a more enlightened manner and getting away from rule-based approaches. We're doing a lot on national design guidelines. The specific one is for ports and harbors. In Kobe in 1995, before the earthquake, they were the 6th largest container port in the world, had a tremendous amount of throughput of containers going through the port. The earthquake knocked out that capability. They are now 38th in the world. And so the moral of the story is the ship sailed, literally, and they went to other ports in the area. So there can be significant economic downsides to disasters shown in the upper left-hand corner. We're also looking at new kinds of technologies, materials, and approaches that allow us to build better buildings and better bridges, things like that, but at reasonable costs. A big thing are existing buildings. There's a lot more existing buildings than there are new ones. And legally, there are limited things we can do, either here in the U.S. or in Japan, to buildings that are privately owned, surprising to say. So it's a real challenge to try and get mitigation technologies out there and in place. but this is the cathedral down in Christchurch. One could superimpose the national cathedral here. There are impacts, even to moderate earthquakes like the one in Christchurch or the one in Washington, D.C. So there's a lot of information to get out there. The question becomes then, what are the immediate needs? What do I study? What do I do? How do I assign these? I don't have unlimited money. Nobody does anymore. How do I do this in a way that has the biggest bang for the buck, the biggest impact? And these are the same questions asked here as well as in Japan. These have been identified in terms of the research world through independent studies in both the U.S. and Japan. Japan has a very orderly process. They just completed a 5-year program called the Daidai Toku program, where they identified national priorities to be looked at. The NEHRP agencies are looking at ongoing work from a practitioner side and a U.S. perspective to look at problems and solutions. We're overlaying that with the academics and government researchers, as well as practitioners, to blend this into a common vision that we're updating at intervals. It's a continuing moving target. We throw in some earthquake reconnaissance work. UJNR is a U.S.-Japan Natural Resources Committee. It's been active since the 60s. This is a government-to-government information sharing. We're also using that channel, as well as NEES and what I'll explain here in a minute, e-defense, cooperative research programs. But in terms of a broad brush, the big things we have to look at now are systems problems, soil foundation structure problems, structural, non-structural problems like happens in every earthquake, lateral gravity systems interaction. I'll show you some pictures here in a minute. The daunting task of existing buildings that maybe don't have adequate systems in place, don't have the innards of the columns and beams necessary to really perform well. We have a frequent problem with no drawings, either in Japan or in the US. Drawings disappear after 20 years or 30 years. And there's also the L word, liability and monetary concerns. In terms of a priority on tsunamis, what can I say? The improvement in prediction models is a key thing, as well as warning systems. You can't give warnings too early because people ignore them, and the warnings have to be reliable. How do you evacuate people? The current thinking now is you evacuate upward to get out of the wave, but that assumes the building you're in can take a significant hit from a tsunami. Impact analysis models to predict how far a wave is going to come in, how high and how far it will run. Community planning and siting, urban planning, where you allow cities to be built, and then can you mitigate effects on a local basis to steer the waves into other less populated areas. Big problem in the structures world are sensors. How can I detect damage better? I was in Japan a week and a half ago looking at damage. I could have done that 1,000 years ago using the technologies that we were using, right? We're really at the forefront of looking at this in an enlightened manner. We need to be able to do real-time and post-event sensing capabilities inside the members. We have to identify changes. You know, what was is not what is now. Is that necessarily bad? How do I handle data? Systems that we have in place now are overwhelmed with data. High temperature and aggressive environments, the radiation problem being a case in point. These kinds of projects need to be a priority. Also, this leads right into active control. Can I put in systems that will modify the structure so that I can respond to the particular ground motion that's coming in. This is the next step. Can I intervene actively? Can I put in a control mechanism that can really ride the wave and instruct the building how to modify damping, stiffness, and even the placement of mass so that it minimizes the amount of response and damage. Big problem is power. How do I make sure that everything works? I mentioned the systems question. Up until now, we've had very limited capabilities in terms of experimental facilities. There were 3 earthquakes that were game changers. The Kobe earthquake in '95, Northridge in '94, and Loma Prieta in '89. Those were large economic events. There was significant loss of life in Kobe, but there were also companion economic losses. Together, those are losses we can't sustain anymore, you know, and as developed countries get better in terms of earthquake design for structures, the loss of life generally decreases. That's what we found in Japan, that's what we found in the United States. Economics becomes a daunting question. So how can we do this? And the answer is let's build some economically viable, large-scale testing facilities. In the U.S., we came up with the Network for Earthquake Engineering Simulation funded by NSF through congressional action. It's a set of distributed experimental facilities, 14 in all, with advanced IT linking the systems, allowing the systems, the different laboratories to talk to one another with experimental and computational data repositories so that I can look at content 20 years from now, be able to look at results with new capabilities down the road. At the same time, Japan established the E-Defense Laboratory near Kobe. Their response was one lab that was, in a word, huge. Largest shake table in the world to simulate ground motions with unmatched capabilities. So here's a shot of the network in the United States. Distributed capabilities, very specialized. Here's the E-Defense facility in Miki City, Japan. That's a 10-story building that's hollow, allowing me to test very large-scale structures. Here's a wall test done at the University of Illinois, using load simulators up the orange blocks up above. Here's a shake table test at the University of Buffalo. Those are full-scale housing units where they did a number of tests looking at residential structures. Here's one done at the shake table at the University of California, San Diego. This is a 1 million-pound specimen, half scale, of a typical system deployed in Los Angeles. A number of these were damaged in Northridge. You can see the scale with the humans down here. So very large scale tests. We couldn't do this kind of before. And then to be humbled, here's a test run at E-Defense. This is a U.S. test of what was called Kneeswood. That's a full-scale apartment house. And to give you another impression, see the guys standing around down here? That gives you an idea of the scale of this thing. Full-scale model, assembled and constructed outside, moved inside with a couple of large bridge cranes, put on the table, and shaken so that everybody on the planet could look at it. And interesting stuff, part of the partnership that exists. The question is, are we making progress? We've been investing, US and Japan, lots of money over the last 40 years, 30 years, in improving our ability to design against earthquake. The Japanese have a slightly different approach because they have a much higher frequency of large events. But generally speaking, we've gotten better. We've gotten a much more robust building environment now based on these new rules. And here's some before and after. Here's a damaged column at the physics building at Tohoku University in Sendai. This building is 1970s vintage, maybe early 80s. This is a damage pattern you see all over the place in older buildings. We know how to fix that. The problem is this is an existing building. It's expensive to fix these things before you really have to. Here's damaged wall elements. You can see a characteristic X cracking pattern. This may or may not be a problem, but it certainly doesn't make the residents of this building sleep any better. This is an interesting slide because it's a before and after. There's a left-handed building, there's another building that forms an L, and then there's a newer building, okay? The older building, as you can see, has crunched wall elements. It's not in danger of collapsing, but it's got lots and lots of damaged elements. It's going to cost a great deal to repair this building. This is the second large earthquake it's been through, and the building is probably done. It's done its duty. It's 15 stories high. It's going to cost a great deal just to demolish it. Here's the companion building, and you can see that this should be a straight line going up, and it's leaning, right? There's a foundation failure. The right-hand building's also damaged, but it's done. We can't lift the building back up into place to make it vertical again. We're not into the Leaning Tower of Pisa. So both buildings have got to come down. The right-hand building is a newer building that was base isolated. I'll show you what that looks like. Floating on isolators. Other than some problems out in the parking lot, it's undamaged. So here you have, 30 years ago on the left where you're done. You're going to be torn down. On the right, undamaged. People are still living in the building and they're happy. This is a public housing unit in Sendai with similarly crunched wall elements. Not necessarily in danger of collapse. In fact, the building is repairable, not because of the initial construction, but because the government came in beforehand, put in a frame, and these yellow things are dampers, like the shock absorbers on your car. They absorb the motion and they gradually damp it out. That saved the building, saved a lot of people as well. This is a shot of a government building. Only an engineer would show a slide like this. But what you have is you have a building on the right side with the columns coming down, and they're sitting on isolators that allow the building to move. This left thing is like a big retaining wall. It's what's known as a moat. And the moat is where the services come in. Water, electricity, sewer, and they have very nice flexible things because the building moved about 20 inches during the earthquake. And that's because it's sitting on rubber lead bearings that allow the building to move. It can translate. Can't translate too far, but it can translate. And it's got dampers. This goofy looking thing is filled with lead, and the lead is a damper that gets damaged that allows the motion to die out. Right-hand side is one of these isolators. Last slide, here's a shot of a government building where they went ahead and retrofitted it beforehand with some very interesting braces on the outside. No damage to the building. So we're making progress. It takes time, money, cooperation, patience, and hard work, but it's important to do right. This is a school that's out of action because of earthquake damage, and this is a little girl's bike with training wheels, and she's not able to live in her house anymore because it was damaged during the earthquake. So there are important reasons to do this. So thank you.
So thank you very much. So now we start the discussion. So if you have some questions or comment, raise your hand. Any question? Yes, please. Here. I'll ask you to give your name and solutions.
James Miller from the FCC. I had a question. If you could talk about the state of the art right now between robots that are autonomous mission execution side versus how much kind of store and forward capability they would have, what the relationship is between that and kind of the radio links that you were using. We saw you identified a couple of frequencies, but I wonder how long can you leave the robot separated from some kind of communications tether before it tends to break down? I know there's probably space applications with some reference to that. But.
Well, the robots that we have, we specify them with two different operating frequencies, and one of them is 2.4 gigahertz and the other is 4.9. We specify that outside and line of sight operation, that we can operate them up to about 800 meters away. After 800 meters, or if you're in an area with a lot of obstructions, like an urban area, of course the radio communications is a lot less. It's hard to give you a definitive specification on it. It just depends. We've recently introduced this new COFDM, COFDM as it's known, package, which gives you a lot better radio comms in urban areas because of the way it bounces the signals and uses multiple frequencies. Does that address your question, or is there some part that I missed there?
More to the machine learning and kind of the aware 2.0 side of the equation. How much is the robot able to autonomously operate without a comm link direct, real time, all the time?
Okay, one of the features we have, and this may address some of that, is what we call retro-traverse. So if the robot's going out and it loses communication with the operator, it will automatically stop and back up until it regains communication by itself. So this is a semi-autonomous behavior.
Perhaps I can add a little bit to that. I mean, communications is a big challenge for every robot. I think it goes way back to the beginning of robotics. It's still a challenge now. And it's simply basic physics. There's only so much distance you can get given a certain power output and all the electromagnetic environment that blocks it, or not having direct line of sight. So, you know, we're working very hard with comms vendors. We're trying not to work directly ourselves on that because it's a field by itself, but integrating the best radios that are out there. But still, the physical limitations remain, and that's in part why we also want to push more towards more autonomy, because that reduces the bandwidth requirements. If you do pure teleop, you're so limited. You require a high bandwidth comms link because you need high quality video, because all the robot is doing is informed by what the teleoperator can see. So you don't only want to get a high definition video to the front, you also want high definition video to the back and to the side and up and down. You want lots and lots of bandwidth to do a good job. And especially if you want to do any kind of haptic teleoperation with manipulators. Now you need not only high bandwidth, you also need low latency. So lots of challenges there. And that's where autonomy comes in, because it relieves some of those bandwidth requirements. As you saw in the video I showed, like the map-based interface, once the robot gets a data point, it can work all by itself until it reaches the data point, the location, and then comes back and say, well, what do you want me to do next? And in between, you could just have no communication whatsoever, in the worst case. Of course, the operator always wants to know what's going on. but it drastically reduces the bandwidth requirements.
Another point that I could mention too, related directly to Japan, is that Japan has very strict regulations when it comes to output power and frequency range. And we had to get special permission from the Japanese government to operate our radios in Fukushima, because they operate at much higher power levels here in the US than would be allowed in Japan. So now on all subsequent robots that we ship to Japan, we have to have Japanese compliant radios in them. And we're in the process of working with an outside test house to give us that capability.
Okay, thank you very much. Okay.
Good morning. My name is Charles Ferguson with the Federation of American Scientists. Very interesting presentations from all of you. Really enjoyed it and learned a lot. So I have two questions. One question involves the Fukushima Daiichi accident itself and the use of robots. So I'm wondering if we could have had 4 deployed robots at that plant and other plants of potential concern, especially the older boiling water reactor Mark I designs. Because if you think about what happened in terms of the sequence of events right after the natural disasters hit on March 11th, within 24 hours, reactor unit 1 was already in a very serious condition, was already experiencing a meltdown. So, you know, if you were shipping in an iRobot from Massachusetts, it's going to take too long to get there. So if you got 4 deployed robots, and you could have people trained to use them, you might even have robots actually inside the reactor building, so you can get on-the-scene information, because it's very chaotic. Instrumentation was faulty, and the operators tried their best, but didn't have enough information to know that start to open up the pressure relief valves. And there's difficulty opening the valves because of loss of electricity. So perhaps you had some of those strong warrior robots, you could have helped use that to open up some of those valves and prevent the more serious meltdown. So that's a somewhat long observation and a question. And the second question goes to both of the gentlemen in iRobot and to Professor Hashimoto in terms of collaboration and training. So you looking at what Waseda has to offer in terms of the expertise and R&D on robotics and the students, professors, and matching them up with the expertise here in the United States to get the more, maybe you're already developing this, but I'd like to hear more about a formal relationship to get the kind of training involved to make sure that, you know, Japan and other countries has the capability to deal with these kind of natural disasters in the nuclear accident.
Well, let me try to address both of those, and then I'll default to Martin here for his comments too. But they're based on what we've learned out of this and the way these events unfolded. There's no question, certainly in my mind now, having been a part of it, that it would make a lot of sense to have robotics teams. Maybe, I mean, ideally, from a robot supplier, I'd like to see robots at every facility, everywhere, in every home, okay? But we know that's probably unrealistic. But I think it does make sense to have robot teams who are trained in, with ongoing training, so that when an event happens, they're prepared for it. And those could be regional. Here in the United States, you could have 6 or 8 or 10 of these teams located around the various regions. You have, as you know, over 100 reactors here. There's 54 in Japan. And I think regional response teams that are trained in robotics and have all the robots with the right types of tools makes a lot of sense. Second part of your question, in an ideal world, there's a lot of talk, and I'm sure Professor Hashimoto and Uchida-san know very, very well what's going on in Japan right now regarding the whole issue of robots and disaster robots. There was a program back in 1999 where the Japanese government allocated a large amount of money for the development of robots. 6 companies responded to that and developed those robots. The robots were actually never deployed, and in fact ended up in museums around Japan. They're in robot museums at various places around the country. After the earthquake, they tried to resurrect those robots, but of course they're 10, 12 years old. They built one of them, of each one. They were never field proven, and they weren't able to use them. What I would like to see, and what I think makes the most sense here, is rather than see Japan go off and develop another round of disaster robots, take a field-proven platform like ours, and don't reinvent the wheel, but on top of that platform, put the sensors and the capability that would adapt it to the Japanese requirements. So use the best of both worlds here. And we're very open to working with any number of private companies or universities in that area.
It is very important is to distribute the robot, maybe iRobot, to the world, the low cost. And also another important thing is how to make a standard interface between the human operator and robot. So something like PlayStation game machine is very good interface between computer and human operator. And in the future, maybe as I showed in my slide, that the robot need not a license to be operated, to operate. So all the people should operate, can operate in the future, like automobile, right? Something like that. So from the very young people to the old people, and so our research dream is, the final dream is to make a robot having intelligence like human, because we can expect every human to have ability to communicate with human. So if the robot has the ability to communicate with human like human being, then it is very easy to operate. So that is very related to the first question, that if the machine learning, the ability is much more developed, then autonomous function will be improved much more. So the communication with radio wave is very less. Only one command, then the rest is autonomously operated by the robot. This is the final goal. Any question? Comment? Martin?
Well, perhaps just to follow on with Mr. Wanda and Mr. Hashimoto was saying, in terms of not reinventing the wheel, I think there's actually an opportunity here for a nice symbiosis between academia and industry, because the currency of academia's research and innovation and publication, and it's difficult to do that really in the direction of developing a platform that's reliable, that has logistic support, that may be radiation hardened. Those are all very important things for disaster robots of fielding, but they're not always that much valued in a research environment, because they tend to be more the kind of things that companies do. That's why I think there's a good opportunity to work with companies and free the universities to work more on the longer term things, like we have huge challenges with perception, with autonomy, user interfaces. So that can all be part of the add-on, the value added to these platforms that universities are very good at, and Japanese researchers are excellent at.
Okay, yeah, please.
Good morning. My name is Yuki Imamura from Washington Study Group. I'd like to congratulate the US-Japan Research Institute as well as the panel, because this is the only panel which addressed the technology related to disaster. But you will be one of the two in next 10 days, because the group which I chair, which is called the Washington Innovation Network, will have another panel related to the technology's role of disaster. So if you're interested in that, please let me know, then I can give you more information. But I will have 3 panelists, 2 who are involved in the disaster management and the development of the software for management software, and some of the third one is the guy who is knowledgeable about the Japanese disaster management. But having said that, I have a question to Professor Hashimoto and probably to Mr. Rondo. As you mentioned, that the technologies before and after disaster. And also one of the issues in Japan has been the in Japanese sotegai, which means everything or many things in disaster are beyond predictability. Well, if you say that, you could excuse everything. So I just wonder how the technology could help unpredictable to be more predictable. And then the question to Mr. Rondo is, it sounds still mysterious to me in the case of deployment of your robots, because you said you didn't have the agreement, any formal agreement with whatever the parties in Japan. Does it mean that you just deployed at your own discretion? Because at that time, the Japanese government really refused any assistance from outside of Japan because they believed they could do everything by themselves. But that wasn't the case. So you really didn't have any agreement or understanding with any parties in Japan either before the right time that when you deploy your services. Thank you.
Yeah, thank you very much. Thank you very much for a very difficult question. About the first question, yes, in Japan, many people say that this is out of imagination of the people. So this excuse of especially for the scientists and also technology people. So in my feeling, this is something like a characteristics of the science itself. Because the science, they consider everything with under something like a definition of the space of the theory or something. So this is the nature of science. Science means the present science. So that in my feeling, we should extend our imagination beyond the definition. This is very important. So how to do it? It's very important, but I have no answer right now. But the most important is how to make the flexible thinking way to our brain itself. So of course, it is very easy to develop the science and technology under the definition. But out of definition is much more challenging. And it is maybe, I think, such a way of thinking will create a new science or new technology or to a new engineering if we overcome this definition, the limitations. So my answer is that to create a new way of science consideration, science thinking is very important to overcome the limitation of the definition. We start from the definition, but something like literature or the poem will not start from the definition. They start from their own expression. So this is very important. So, and there are some possibility to create new type of science and engineering. This is my answer right now. Then about the second question, please, Troy.
Okay, you asked a very good question. And I think the easiest way to answer that is to maybe tell you a little story about how this whole thing evolved. The earthquake occurred on the 11th. Over the weekend, I received a phone call from our distributor in Japan, Sojitz Aerospace. Now, about a year earlier, there are many trade exhibitions and conferences about robotics around the world. And one of the largest ones is held right here in the Washington area, and it's called AUSA. It's a very big military-related exhibition, of which iRobot participates in. At that exhibition, there was a delegation from Japan who attended. They were a group of high-ranking officers from the Ground Self-Defense Forces. They saw our robots. They played around with them a little bit at the exhibition, and of course, went back to Japan with a lot of information about the robots. So when the earthquake occurred, one of these officers contacted our representative, our distributor in Japan, and mentioned, do you think that the iRobot products could help us in some way? So our distributor came to me and said, I've had this request, what do you think? So I talked to some of my managers, and before I knew it, within 24 hours, our CEO said, let's send robots. We can help with this situation. So over 2 days, we had people working around the clock to assemble the robots and all of the other equipment that we needed to go over there. Because again, we had no idea what was going to be required, none. And we got the export license, as I mentioned, in 24 hours. And the actual user on the export license was the Ground Self-Defense Forces. So we shipped the robots over, and we told our distributor, the robots are coming, and we're going to send 6 people along with them. Well, that was the good news. The bad news is nobody knew who was going to accept these robots, all right? So over the next day, through some help with Sochitz Aerospace and some leading politicians in Japan, it was decided that when the robots arrived, they would be given to TEPCO to try to help with the Fukushima Daiichi efforts. So that's what we did. But there were no formal agreements or contracts or purchase orders or anything. These were totally donated free. Along with everything else. Now, just recently, we have formally transferred the ownership of all of that equipment to TEPCO. So they are now officially the owner of those 4 robots. And as you might imagine, we will never see those robots again. They are heavily contaminated now, and they will never leave the Fukushima area. And honestly, we don't want them. We're also, Martin mentioned in his talk about our underwater robot, our sea glider. And recently, we put a radiation sensor into the sea glider. We finished the testing of that now, and we're ready to deploy it. And we're hoping that by the end of the year, a couple of sea gliders are going to be deployed in the ocean off of Fukushima to look for doing radiation measurements in the water. Thank you.
Hi, my name is Naoto Oka. I'm with Arborata. My question is that when I look at the iRobot robots, they are kind of ugly and cute. They're very functional, and you don't care essentially how it looks as long as it works. When I look at the robot from Waseda, they try to simulate the human body, like a real human. And I see other robots in Japan which look like humans, Of course, in factories in Japan, there are robots just with functionality. But I'm wondering if there's anything cultural that Americans don't care how the robots look, and in Japan they care a lot to make it look like humans.
Well, Martin, why don't you address that, or I can give you my opinion. Our robots were really initially developed as a result of contracts from the U.S. government to support our troops in Iraq and Afghanistan. They were designed for a specific purpose initially, and that was explosive disposal, to help soldiers who had to deal with IEDs and bombs so they wouldn't be injured by these things. So the main purpose of those robots, I think, is very, very different than the robots that I've seen in Japan, and I agree with you. There's this tendency to make robots that look like people, and they have nice smiling faces on them and things. But Japan never really developed robots for military purposes because the country doesn't have an really active military effort. You participate in peacekeeping operations around the world, but you don't participate in things like we do at times. Whether you agree or disagree with that doesn't matter. So our robots are functional for a purpose. We don't need to have a robot that has the aesthetics that some of the robots in Japan have, because they were designed for totally different purposes.
Yes, actually, maybe in the United States, the robot is a tool for something for human. But in Japan, not all, but many people, the researchers, thinking that the robot is a colleague or friend who will live with us in the home. So this is quite different. So this may be the influence of the Astro Boy or something. Now the researchers, when they were child, they are very familiar with Astro Boy. So this is maybe the DNA of the robot researchers in Japan. So this is quite different, but sometimes the same. Go for the tools to make a very, what shall I say, the excellent tools. We have to make another shape of the robot that is very fit to the tasks. So especially in the medical application, we do not make a human-like robot for the medical application. That is a tool of the medical doctors. That is the hand, that is the eye, and that is a finger of the doctors. So this is quite different direction we have in this case. So it depends on the situation. So other questions? Yes, please.
Good morning or good afternoon. Alan Manuel, Federal Communications Commission. Question for Dr. McCabe. So with research and development, best practices and standards, and while you're not responsible for this part of it, what do you see on the engagement and the implementation from the end user? In our country, it's the state and locals that control zoning and building. So what do you see, because that process is application with other technical fields? Thank you.
Excellent, excellent question. That's always the big issue. You know, we can develop all kinds of standards. We can develop best practices from a national standpoint, but ultimately it comes down to the states and the local entities, the cities, the counties, to implement those standards. And the history is mixed. California and the West Coast have the luxury of having lots of seismic activity, as does Japan. So it becomes a relatively easy sell to embrace these new technologies and these new rules, because there's a very definite, immediate kind of impact. The rest of the United States is less concerned about earthquakes. So it's been and continues to be a real education problem in terms of getting the word out and attempting to convince local political entities, city councils and state agencies to really push for these. There was a building code revolution in the United States in 2000 where the International Building Code was implemented. That greatly increased the capabilities of the building codes, but there are still wide areas of the country that lag behind in terms of active implementation of all of the regulations. And it's a difficult problem because there's a separation between the federal and the local states. The downside is if you don't implement these things, then it's at some point up to the federal government to help clean up the mess afterwards. And with the FCC, you have people depend on cell phones. They depend on communication capabilities. If you lose all of the modern accoutrements of society, there's a big problem there. So hopefully over time we can continue to push on this, but there's probably going to need to be some new federal initiatives along this line that would help encourage local adoption and implementation. But it's an on-point question. It's very, very insightful.
Thank you very much. So any other questions or comments? Okay, no questions. Thank you very much. So I'd like to thank again for the coming of all of you, and we had a very good discussion. And I hope you have some ideas or a new hint about these issues. And also I'd like to thank the three people, Martin, Roy, and Steve, for coming and a good presentation. Thank you very much.